Hi everyone, I thought I would go over homework number 59 with you today. This is about increasing, decreasing maxes and mins um, as we start the mean value theorem section. Our problems start on page 206 and 7. This is assignment number 59, and we're starting with problem number 15. Okay, 15. F of x equals 5x minus x squared. F of x equals 5x minus x squared. And we're asked to find part A, any local extrema, part B, where the function is increasing, and part C, where the function is decreasing. Okay, so remember, to find extrema, we're looking for places where f prime changes sign. And that can happen at critical points where f prime equals 0 or is undefined. We could also check endpoints of a bounded interval, but none of these first problems have bounded intervals, so we don't have to worry about that, which is why it says find any local extrema. Yeah. Okay, so let's start by finding f prime. That'll be 5 minus 2x, and we set f prime equal to 0 because when I look at this is a linear equation, and that's never undefined. So 2x equals 5, or x equals 5 halves. Okay, so I have a critical number, 5 halves, from my f prime sign chart. If I plug a 0 in here, I get a positive, right? 5 minus 0 is 5, that's positive. And if I plug something bigger than 5 halves, like 3 in here, 2 times 3 is 6, and 5 minus 6 is negative 1. So I see part A, there is a max at x equals 5 halves on f of x, because to the left of x equals 5 halves, f prime is greater than 0, and to the right of x equals 5 halves, f prime is less than 0. Remember, we're going to need to write our justification sentence for every single max and every single min for the rest of the year, because you'll be justifying this on the AP exam. B, we're interested in knowing when this function is increasing. Well, f is increasing on negative infinity to 5 halves. Why? Because f prime is greater than 0 on negative infinity to 5 halves. So whenever f prime is positive, we know f is increasing. And likewise, f is decreasing on 5 halves to infinity, because f prime is less than 0 on 5 halves to infinity. Okie doke. All right, next we've got 17. 17 says h of x equals 2 over x. H of x equals 2 over x, or 2x to the minus 1. So h prime of x is going to be negative 2x to the minus 2, or yes, x to the minus 2, or negative 2 over x squared. Well, I see that this function is never going to be equal to 0, so let's just confirm that for you. Oh, I multiply by x squared. These cancel, and I get negative 2, and over here I get 0. No, that's not true. So the derivative of h prime, is never equal to 0. But the derivative would be undefined at x equals 0. So x equals 0 is a critical point on my h prime sign chart. And if I plug in a negative here, remember it's h prime that we're plugging values in. If I plug in a -1, that's going to be squared and turn into +1. And I'm going to have -2 over +1, which is negative. And over here, if I plug in a +1, well, the same squaring happens, and I still get a negative over a positive, which is a negative. So part A, no extrema. And how do I know there are no extrema? Because I see no sign changes on H prime. I need a sign change on H prime in order to know that there's going to be a max or a min. Right now, H prime is going from negative to negative, which means decreasing and then decreasing. And of course, our original function doesn't exist at 0. There's a vertical asymptote there. Okay, so, I mean, we already know what this looks like, right? Oh, look, decreasing. Oh, look, decreasing. All right, so we know there's no extrema. Part B, when is this function increasing? Never increasing, because H prime is never greater than 0. But when is H decreasing? H is decreasing on -infinity to 0, union 0 to infinity, because H prime is less than 0 on those intervals. Okay, that's number 17. What about 19? 19. We've got f of x equals e to the 2x. F of x equals e to the 2x. Well, we know from our work with the chain rule that the derivative of e to the is e to the, and then we take the derivative of the inside function. Now, we know that this derivative is never equal to 0 because it's exponential, right? We've got this, oops, wrong asymptote. We've got this exponential growth function which approaches but never equals 0. And f prime is never undefined either. We know from this, from Algebra 2 and Pre-Cal, that this function is always increasing, never decreasing, and never has any maxes or mins. So not much calculus we needed to worry about here. No extrema, because no sign change in f prime. In fact, if we make an f prime sign chart, since we have no critical numbers, since this is never equal to 0 or undefined, any number I choose, like 0, and plug in, I'm going to get a positive 4. And because of that, I know f is always increasing because f prime is always positive. And C, f is never decreasing because f prime is never less than 0. Okay, 21. 21 says y equals 4 minus square root of x plus 2. Okay, so it's our square root graph shifted left 2, flipped upside down, and moved to the right, moved up 4. Okay. You might want to rewrite this as x plus 2 to the 1/2 power. I know I do. So y prime is going to be the derivative of this, 0. And then the derivative of this, I bring the 1/2 down. Don't lose that negative. X plus 2, and subtract 1 to the minus 1/2. Don't forget chain rule. Take the derivative of the inside function, but here the derivative of the inside function is simply going to be 1. So I end up with 1 over 2 square root x plus 2, and don't lose that minus sign. All right, so here's my y prime. this y prime is never equal to 0 because, look, if you set this derivative equal to 0, you'd multiply both sides by 2 root x plus 2, and then 0 times that is still 0, and over here we just cancel out the denominator. So never is y prime equal to 0, but y prime is undefined when x equals negative 2. Negative 2 gives me 0. Square root of 0 is 0, times 2 is 0, and I'm dividing by 0. So I've got a critical point for my y prime sign chart at negative 2. Now, if I plug in a number like 0, I have negative 1 over 2 root 2. Well, root 2 is 1.4 times 2, 2.8, and so negative 1 over 2.8, well, that's going to be a negative number. But what if I put in something like negative 3? Negative 3 plus 2 is negative 1, and the square root of negative 1? No, that doesn't exist. So, what do you notice here? We have an endpoint. So, this isn't a restricted domain, except for the fact that, well, yes, it is, because the function has a restricted domain. So, what do we have going on here? We have an endpoint, and then y is decreasing. So we have an endpoint, and then y is decreasing. So that endpoint must be a maxima. So for part A, I say y has a max at x equals negative 2 because x equals negative 2 is the left endpoint, and y prime is less than 0 to the right of x equals negative 2. B, when is this function increasing? Well, no, this function is always decreasing. There's only that one critical value, and we see negative to the right of that. So we say y is never increasing because y prime is never greater than 0. But for part C, y is decreasing on negative 2 to infinity because y prime is less than 0 on negative 2 to infinity. And remember, this goes in line with the way we thought about this graph. When we thought about the graph of this, we've flipped upside down, we've shifted left 2 and gone up 4. And so my graph is going to look like that kind of thing, with a max here at negative 2 and always decreasing. Great, that's 21. What's next? 24. 24 says, find local extrema, find increasing, find decreasing. Ooh, but we get something tougher this time. Y equals x to the 1/3 x plus 8. Okay, so in order to find y prime in this situation, we're going to need to do the product rule. All right, product rule. So this times the derivative of that plus that times the derivative of this. X and subtract 1 minus 2/3. Here's the thing we've been trying to get you ready for since August, September of pre-cal, when we need to factor out that smallest power. So we're going to factor out x to the negative 2/3. When we factor a negative 2/3 here, we're going to be left with x times 1, so that's x, then our plus symbol, and here we factored out all of this, but we still have the 1/3 and the x plus 8. Okay? So there's our y prime. Now I need to distribute and combine like terms. So y prime is going to be x to the minus 2/3. 1/3 x plus 1x is 4/3 x plus 8/3. Okay, well, it looks like I can do some more factoring here. I can factor out a 4 from each of these and a 1/3 from each of these. So I'm going to take out a 4/3 x to the minus 2/3, and what will be left? X plus 2. All right, so there's my y prime. Now, the cool thing is, remember how we're looking for y prime equal to 0? Well, that happens when x equals -2. But we also want to know when y prime is undefined. And any of these negative exponent things, remember, they're going to be the same as x to the positive 2/3. Why, look, it's in the denominator. So whenever this is equal to 0, we know we found when the derivative is undefined, and that happens at x equals 0. So we've got -2 and 0 on y prime, and let's check some values. Okay, so remember, we're checking in y prime, not in y. So let's use this tidied up y prime that we have over here, and let's plug some values in, like 1, -1, and -3. Okay, so if I plug in a 1, in fact, maybe I even want to have this. If I plug in a 1 here, 1 to the 2/3 is 1, times 3 is 3, and a 1 up here, 1 plus 2 is 3, times 4 is 12, 12 divided by 3, that's positive. If I plug in a -1, however, what's -1 to the 2/3 power? Well, let's confirm it, but I think it's +1. -1 raised to the 2/3 power. Yep, +1, because we're going to be squaring. Even though I could take the cube root of a negative number, that squaring is going to turn that negative into a positive. So I end up with a positive on the bottom, and on top, when I plug in a -1, -1 plus 2 is +1. So I have positive on top, positive on the bottom, so I'm still positive over here. Okay, and then what about here with -3? Okay, well, -3, when I take the cube root of a negative, I get a negative, but then I square that number and I get a positive. Times a positive, I have a positive on the bottom, but -3 plus 2 is -1 on top, times 4, still negative over a positive, and that's negative. All right, so what do we see here? We see there is a min on y at x equals -2, because to the left of x equals -2, y prime is less than 0, and to the right of x equals -2, y prime is greater than 0. We have no sign change here at x equals 0, so we don't have a max or a min there. My guess is that if we did the second derivative, we'd find out that there's in fact an inflection point there. What else did we need to find? When is this function increasing? When is this function decreasing? Okay, well, I know that this function is increasing. Y is increasing on -2 to 0 union 0 to infinity, because y prime is greater than 0 on these intervals. And part C, when is y decreasing? Y is decreasing on -infinity to -2, because y prime is less than 0 on -infinity to -2. Okay, so there's number 24. How about number 25? H of x equals -x over x squared plus 4. H of x equals -x over x squared plus 4. That's a great question. Okay, so you could use the quotient rule, or you could rewrite this as -x x squared plus 4 to the minus 1. I don't know. I kind of prefer this and use the product rule, but I don't know that it really matters. So just to satisfy curiosity, I'm going to find h prime by using the quotient rule. Low d high minus high d low over low squared. Okay, let's tidy some things up. We're going to get a positive 2x squared minus 1x squared is 1x squared, and then minus 4. And on the bottom, x squared plus 4 squared. Okay, so this is always positive. It's a parabola shifted up 4, and then just if you didn't believe that was always going to be positive, we're going to square it anyway, and so it's really always going to be positive down here. This is never equal to 0. This is always positive, so the derivative h prime is never undefined. But the derivative would be equal to 0 when the numerator was equal to 0, and that happens at x equals 2 and negative 2. So we've got two critical values here on h prime, and let's plug in some values like 0, 3, and negative 3. And remember, this is an h prime sign chart, not an h sign chart, so I'm not plugging them into h, I'm plugging these things into h prime. Alright, so if I plug in a 0 here, I end up with negative on the top and a positive on the bottom, that's minus. If I plug in a 3 here, I have 9 minus 4, that's positive 5 on top, positive on the bottom, so I get a plus there. And then finally, if I plug in a negative 3, I square it, I get 9 minus 4, still 5, that's positive over positive. So I end up with part A, there is a max on h at x equals negative 2, because to the left of x equals negative 2, h prime is greater than 0, and to the right of x equals negative 2, h prime is less than 0. And what else? Well, there's this min over here. There is a min at x equals 2, because to the left of x equals 2, h prime is less than 0, and to the right of x equals 2, h prime is greater than 0. So there I've justified my extrema for part A. Part B, intervals on which the function is increasing. Okay, well, I see the function is increasing. B, h is increasing on negative infinity to negative 2, union negative 2 to infinity, because h prime is greater than 0 on these intervals. And finally, we're asked when is h decreasing, and we know that h is decreasing. H is decreasing on negative 2 to 2, right, from negative 2 to 2, because h prime is less than 0 on negative 2 to 2. All right, that was number 25. Next we have 27. 27 says, ooh, look at this. I don't know, what do you think? Is this a I must use a calculator problem? Well, let's see, x to the third minus 2x minus 2 cosine x. Okay, so again, I have to find f prime. And when I look for f prime, I say, well, that's going to be 3x squared minus 2. And the derivative of cosine is minus sine times negative 2 is plus 2 sine x. Well, I have no clue how to set this equal to 0. So I know this is a calculator question. So let's type in our function into y1. We've got 3x squared minus 2 plus 2 sine x. And I'm just going to check my mode to make sure I'm in radians. Good. And I'm going to do zoom standard because I have no idea. I expect it to vibrate up and down, but I expect it to kind of be parabola-like. I don't really see a parabola here. Shouldn't a parabola go up and down? That's troubling. Okay, well, let's try zooming out. You hear that? Oh, look, there's a little wiggle there. Yeah, well, that's interesting. Could there really only be one x-intercept? Well, let's think about that. If I plug in a negative number here, I'm supposed to get a positive. Why is this showing me negatives? And when I put in a negative here, I get positive and negative numbers. So I don't get it. Zoom 6. Makes me want to make sure I typed it in right. I didn't. Squared. Okay. Graph. That's better. Alright, and if we look close, we'll notice that this thing is vibrating some. But I see some zeros, so let's find those. In fact, I think I'm going to make my viewing window a little smaller. -3 to 3, and -3 to 3. Okay, so I can calculate, I can calculate 0. Bring my cursor close to that x-intercept over there, and to the left of it, enter. To the right of it, enter. Guess, no. And so I get x equals -1.126. -1.126. Okay? And then let's find the other one. Climbing back up now. I'm on the left side. I hit enter. Oh, no, that's not going to work. Try again. Left side, move the cursor. Right side, hit enter. Guess, hit enter. And I get x equals 0.559. This is certainly something you should be able to do on your graphing calculator. In fact, when we look at the graphing calculator at our f prime graph, it kind of looked like a parabola. And that means we can see without testing values plus, minus, plus. Right? The parabola is above the x-axis, so f prime is positive. The parabola of f prime is below the x-axis, so f prime is negative. And the parabola of f prime is above the x-axis, so f prime is positive. So we can answer our questions easily enough. Part A, there is a max at x equals -1.126 because to the left of x equals -1.126, f prime is greater than 0, and to the right of x equals -1.126, f prime is less than 0. There is a min at x equals 0.559 on f of x because to the left of x equals 0.559, f prime is less than 0, and to the right of x equals 0.559, f prime is greater than 0. All right, what about increasing and decreasing? Okay, we're looking for increasing first. So f is increasing on negative infinity to negative 1.126 union 0.559 to infinity because f prime is greater than 0 on these intervals. And when is f decreasing? F is decreasing whenever f prime is negative, so from here to here. So we can say, for part C, f is decreasing on negative 1.126 to 0.559 because f prime is less than 0 on this interval. Okay, that's 27. We've only got 5 more problems, and I recall them being pretty straightforward, though they are antiderivative problems. Find all the possible functions f with the given derivative. So in these problems, they're going to give me the derivative f prime, and they're going to ask me, what's f? Well, whose derivative is this? That's the derivative of 2x. Oh, but wait a minute. Couldn't it be the derivative of 2x plus 5 also? Couldn't it be the derivative of 2x minus 7 also? So we have to say whenever we go backwards, not only this, but plus c. That plus c allows for us to take the derivative of the constant and get a 0. So remember, when you go backwards, always add the plus c. Okay, 31. 31, we're looking at f prime equals 3x squared minus 2x plus 1. Okay, so what would f be? Whose derivative is this? Oh, that's the derivative of x to the third. Minus whose derivative is this? Oh, that's x squared's derivative. And whose derivative is that? That's the derivative of 1x. Don't forget, when you're going backwards, you need that plus c. You've got to have that constant when you go backwards, or you will lose the answer point. 32. F prime equals sine x. F prime equals sine x. Well, whose derivative is sine? Not cosine. Cosine's derivative is negative sine. So f must be negative cosine. And you know, when you're not sure, like, well, maybe we weren't sure about this, you can always test by taking the derivative of what you got. So what's the derivative of cosine? It's negative sine, and then we have a negative out in front. Minus times minus is plus, and there we go. But what shouldn't we forget? Don't forget the c. Okay, 33 says f prime equals e to the x. So what's f? Well, that's e to the x plus c, because we know that the derivative of e to the x is itself. And then 34, we have something more of a challenge. Whose derivative is 1 over x plus 1? And that's going to be f of x equals ln of x plus 1. Now, notice in the book it says for x is greater than 1. So we don't actually need the absolute value. We can get away with parentheses here. But don't forget, we're going backwards, and so you need a plus c there. And if you don't believe me, take the derivative. What's the derivative of ln? Of stuff, 1 over stuff, times the derivative of stuff, which is 1. There we go. Oh, and don't forget the derivative of a constant is 0. All right, our last problem, problem 53, is a true-false question, a multiple choice question, rather. It says, if f of x equals cosine x, then the mean value theorem guarantees that somewhere on 0 to pi over 3, what? What are we guaranteed? Well, we know that f of x is continuous everywhere. We know that f of x is differentiable everywhere, certainly on this interval. So let's use our knowledge of MVT. We've met the preconditions, right? F is continuous on this interval, closed interval. F is differentiable on the open interval. And so then we know that f prime at some point needs to equal f of b minus f of c over b minus c. And so in our problem, we want to say that this stuff over here, this b is pi over 3, and this a is 0, and our f is cosine. So cosine pi over 3 minus cosine 0 over pi over 3 minus 0. Well, what is the cosine of pi over 3? That's 1/2. The cosine of 0 is 1 over pi over 3. So I get negative 1/2 over pi over 3, and when I flip and multiply, I get negative 3 over 2 pi. And negative 3 over 2 pi is choice A. Choice A is my answer to number 53. That's what f prime will equal. F prime has to equal this number at some point, some x value, on 0 to pi over 3. And for more MVT practice, watch my MVT video. All right, take care, everyone. Happy homework. That wasn't so bad. I don't know why they complained. That was only 36 minutes, and I explained the whole time. Have a nice day, everyone.